So, in the last class we saw experimental aspects of NLEIS. So, today I want to show you how understanding of EIS and NLEIS can be useful. First I want to give you some background. If we do corrosion experiments to estimate corrosion parameters, certain standard techniques are used. We have seen this in the introduction part where we discussed about other techniques. There are certain experiments, one is called potential dynamic polarization, another is called linear polarization, and of course EIS. These three are commonly used to characterize corrosion, but these make some assumptions, and when the assumptions are violated, the results that we get will not be correct. I want to give you some examples, and after that I also want to give you an introduction to another technique called electrochemical frequency modulation, in fact one more technique called harmonic analysis, which are also proposed to monitor corrosion, and we can go through them and see how to interpret the data, what are the limitations of those techniques. So, in corrosion rate estimation, people commonly use what is called Tafel extrapolation, it is called Tafel analysis often. If you imagine that you have metal oxidation, iron oxidizing to iron 2 plus and simultaneously H plus reduction to hydrogen, you can imagine that these two reactions are elementary reactions. They may or may not be elementary reactions, but let us assume that they are elementary reactions. First reaction is called anodic, it is oxidation, and the second reaction is cathodic. When both proceed at the same rate, you will have iron dissolving into the solution and hydrogen ion coming out as hydrogen gas. And this is described by what is called mixed potential theory, where assume this is potential, this is current, in fact log of current, and if it is elementary reaction for fixed concentration, we will expect that current is proportional to the exponential of the potential. So, log current will be proportional to the potential. If I take only the anodic reaction, it would be a straight line in this semi-log plot. If I take only cathodic reaction, it will be a straight line, but with a negative slope, and at this location both of them will have the same rate. So, if I put iron in HCl, then I would get corrosion given by this location where cathodic and anodic reactions are equal in magnitude, opposite in sign of course. And this is called mixed potential theory. We assume the cathodic reaction does not influence the anodic reaction and vice versa, and these are of course assumed to be elementary reactions. This case we would normally write anodic reaction as Faraday constant, K1 is the rate constant, Fe here is the concentration or activity of iron. Because it is solid, we can take it as 1, and K1 we would expand it as K10 exponential B1 E with reference to corrosion potential. And the cathodic reaction we will write it as F K2 H plus square, because it is a second order reaction with a negative sign of course, and again we can expand the K2 and we will keep the concentration. If you assume the concentration of H plus is fixed, it is possible to write this in a simpler form. When we do not apply any potential, the cathodic and anodic reactions are equal in magnitude. You can rewrite this I car exponential E minus E car by beta A. Now, I car is going to be F K10 Fe concentration, and that is going to be also equal to F K20 H plus concentration of H plus or activity of H plus squared. Okay. This notation, which is more common in the corrosion field, beta A is going to be inverse of what we have written as B1, and that is going to be RT by N1 alpha 1 F. N1 here is the number of electrons, 2 electrons. For the cathodic reaction again it is 2 electron N2, but it could be a different reaction. Instead of iron going to iron 2 plus, it could be iron going to iron 3 plus, in which case N1 will be 3, N2 will still be 2 for this reaction. If you have another cathodic reaction, correspondingly the N number will vary. So, I want you to be familiar with the notation that is used in the corrosion industries. People use beta A and beta C, call it as anodic Tafel slope, cathodic Tafel slope. and the total current of course is the sum of this anodic and cathodic currents, it is algebraic sum. So, you get an expression like this, and this is what is used for Tafel analysis. What we measure is the total current. When we do the experiments, we do not measure the anodic current alone or cathodic current alone, we measure the total current. If we go to very positive potential, we can sometimes say that we can neglect the cathodic current, it is not likely to be a large number. If you go to very negative potential, we can say the anodic current is negligible, cathodic current is probably equal to the total current or more or less equal to the total current. Now, beta A and beta C values cannot be arbitrary, because earlier we have seen this, right. It is given by RT by N alpha F. R of course is universal gas constant, T is the temperature, F is the Faraday constant, N1 is the number of electrons, alpha is the charge transfer coefficient, and that can vary between 0 to 1. Okay. So, that means beta A cannot be an arbitrary number. At room temperature, if N1 or N2 that is 1, then B1 can vary between 0 to 39. That means beta A has to vary between 26 millivolt to infinite if its alpha is 0, but very large number. So, it can't be less than 26 millivolt. When you fit this data, you should be careful, you can't get an arbitrarily small number for beta A or beta C. Now, when you do experiments, you will typically go to a DC potential, measure the current, and normally you will scan it at a very slow rate, and you will analyze the data assuming that it is more or less under steady state condition. You change the potential very slowly and record the current. Ideally, you should go to galvanostatic mode, supply a current, wait for the potential to stabilize and note that or record that, and then go to next value of the current and proceed. But most of the time researchers end up scanning the potential at a slow rate and measuring the current and assuming that the double layer capacitor does not contribute that much to the total current, and then fit it to the Tafel equation. It is often called Tafel extrapolation. Essentially take this data, and this is the expression, I total is this. You can use commercial software or you can write your own code and get this parameters beta A, beta C, I0 or I car and E car. E car is very easy to get, the other parameters you can model this and get. Now, you can also calculate one more term called polarization resistance. Okay. That is basically d I total by d E, assuming that you have not scanned it at a fast rate. Ideally, you have just gone to a DC potential, measure the current, gone to another DC potential, measure the current, measure the steady state current, and then if you plot it, if you plot IDC versus EDC, and this is going to be 0 at some potential, and that is corrosion potential. The slope at this location should give you di by de, and the inverse of the slope should be the polarization resistance. So, in this case, if you take this expression, if this expression is valid, you can take the derivative and then rearrange it and then show that this di by de is given by I car multiplied by inverse of beta A and inverse of beta C. So, that is essentially you can rearrange it and then write an expression for polarization resistance. Now, if I get IDC versus EDC potential dynamic polarization curve and fit it to this model, if it fits well, then I can extract the values of I0, beta A, beta C and E car, and I can estimate the value of polarization resistance. So, using this technique, E car is easy to measure, but other three parameters can be measured using Tafel extrapolation, potential dynamic polarization and Tafel extrapolation analysis. Now, it takes some time to do these experiments. If you go to large anodic potential, sample will get oxidized or it may corrode very fast and will get destroyed. We assume that the interface, electrode electrolyte interface is not altered during the experiment, and usually in the cathodic regime it is not altered, but in the anodic regime there is a high likelihood of the surface getting altered. Anyway, if you go to high potential, there is a good chance it will get destroyed, and in some cases it can also passivate, the surface can get passivated at anodic potential. This Tafel model assumes that reaction proceeds without passivation. So, if there is passivation, then you cannot use that data acquired in the passive regime and use this model and hope to get corrosion current estimates. So, another technique that is used in corrosion industry is called linear polarization. In this, we keep the electrode very close to the open circuit potential, corrosion potential. It is slightly disturbed from this. So, we hope that the electrode is not altered too much and it will not get destroyed, and it is considered as a non-destructive technique. When the electrode is very close to the open circuit potential, the current versus potential, IDC versus ADC, can be assumed to be a straight line. Sometimes it may not be a straight line, even near this OCP, open circuit potential, it can be a curved line. It is all right, you can fit it to a curve, maybe a quadratic equation, maybe a cubic equation, but then take the derivative and find the value of the derivative at this location where current is 0, and the inverse of this derivative can still be related to the polarization resistance. So, this Tafel equation or this expression, if we expand it Taylor series and then linearize, we can write it as e power x as approximately 1 plus x, and therefore, we will get an expression like this. You can rearrange it and then divide by del E, a small change in potential, and you can get the expression for polarization resistance. Now, what you can measure using this technique is basically del E by del I. You will not be able to get I car, beta A and beta C from this experiment and analysis. Essentially, you plot I versus E taken near E car, find the slope, inverse of the slope is polarization resistance. But in this technique, the sample is likely to be preserved, it is not likely to be destroyed. And if it passivates at large anodic potential, we do not have to worry, because we do not go to large anodic potential in this technique. So, the problem in this is that you cannot get I car, you cannot get beta A and beta C. You can get polarization resistance value, and if you want to look at the effect of certain chemicals, for example, you have a solution, you have a metal, it corrodes at certain rate, you add a chemical and hope that the chemical acts as an inhibitor. You can find the polarization resistance without the chemical, you can find the polarization resistance with the chemical, and that will give you an idea of the effectiveness of this chemical. Okay. So, in that sense it is useful, but if you really want to know the corrosion current, then you can't get the corrosion current from this technique. If you use EAS, you can acquire EAS without any DC bias, and the low frequency limit will give you the polarization resistance if the solution resistance is negligible. In case solution resistance is significant, low frequency limit is given by Rp plus R solution. So, as an example, in complex plane plot, data may come like this. This is R solution, this is Rp, and this point starting from origin, that is Rp plus R solution, and you can get the value of Rp without any ambiguity here. So, if for example, you are able to take data only up to this, you can fit it to a circuit and extrapolate and see where it will fit. Of course, if you take data only up to this limit, your confidence will not be that high, but you will at least be aware that your confidence is not that high. Here also the sample is not destroyed, it is similar to LP, it is similar to linear polarization, but then you can't get the I car value from this. So, if the solution resistance is not negligible, what happens is this. This is an example. These experiments were done by one of our research scholars. Zirconium dissolving in solutions containing small concentration of hydrofluoric acid. The green colored dots here show you the experimental data, and she has written her own code to model this. The anodic current is given by the red color line, and the cathodic current is given by the blue color line, and the total current of course is given by the black color line. Does not fit very well. This is current versus potential. This can also be shown as potential versus log of current, and this just the same data and the model data with potential versus model current, potential versus current density, and you can see that the fit is not that good. Black color line is the model. Near this region it is deviating, that is not too bad, but even when the current is large, it shows some difference. And if you estimate the parameters, I car is 7.5 milliamps per centimeter square, you get certain value for E car, beta A, beta C, and the polarization resistance coming from this is nearly 21 ohm centimeter square. Now, if you do impedance analysis, if you take ES data, this is what we get. Just note that the x axis or the Z real goes from 10 to 22 ohms, and the imaginary minus Z imaginary goes from nearly 0 to 4 ohms. You can fit it to an equivalent circuit and get the polarization resistance. Right now, I will not worry about the details of what circuit is meaningful for this. We will just say that this circuit fits this data well, and the polarization resistance can be estimated, and you can see the solution resistance plus polarization resistance is about 21 ohm. The polarization resistance alone is about 11 ohms, it is 10.4 ohm centimeter square. So, obviously, this is quite different from what we got from Tafel analysis. So, there is a mismatch between potential dynamic polarization data and analysis versus impedance data. Now, we can do polarization experiments, linear polarization experiment, typically plus or minus 10 millivolt around the open circuit potential, and that is sort of equivalent to impedance at low frequency limit. If we do polarization experiment, we get 21 ohm again. First thing to note is polarization experiment analysis and the Tafel extrapolation, they all assume solution resistance is 0, but what you get out of those, what you get out of this is Rp plus R solution. So, the polarization resistance in linear polarization comes out to be close to 9.5 ohms, which is sort of close to 10.4 ohms. So, between the EIS and linear polarization, one can say that the data is similar. Potential dynamic polarization gives you 21 ohms. So, linear polarization gives you di by dE, and we would normally write it as Rp inverse, but in reality it should be written as Rp plus R solution inverse. Since solution resistance is close to 10 ohms, linear polarization data will give you the polarization resistance as close to 9.5 ohms. The actual slope, if you take the inverse of the actual slope, that is going to be close to 20 ohms. Now, potential dynamic polarization data, the first simplest step is to take the estimate of Rp and say that is actually equal to Rp plus R solution, then get the R solution value from impedance spectra, subtract it, then the value of Rp that you get is going to be close to the correct value. There is a more appropriate way of handling this. When we apply a potential, some part of the potential is dropped across the solution and some part of that is dropped across the interface. The analysis normally assumes that all the potential drop occurs at the interface, but you can incorporate the solution resistance effect by saying the actual potential across the interface is little less than the potential that we apply, and put it in the solution. So, I total, which is on the left side, also comes on the right side, it is an implicit equation. but it is possible to handle this. You can then use an optimization program and get these values. So, we have used an optimization program which accounts for solution resistance, and then if you calculate the value, that comes to be 10.3 ohm centimeter square, which is comparable to what you get from impedance spectra or from the linear polarization. I want you to note that the fit is still not good even after accounting for solution resistance, and that is likely because the hydrogen evolution reaction or the zirconium dissolution, neither of them are elementary reactions. So, we do not expect the kinetics to follow exponential rate versus potential all the time. This will give you an idea of what the corrosion rate is going to be. For comparison with other situations, this is probably useful to get the absolute value of corrosion current and estimate the weight loss or corrosion loss. This is probably not going to be the best choice, but then if you have to make an estimate in a short time, this is probably a good choice. So, this is a more appropriate method. You can always take the polarization resistant estimate and subtract the solution resistance. You will get a better estimate for RP, but the values of beta A and beta C that you get from the previous case will not be correct. Okay. So, it is better to use the proper equation which accounts for solution resistance or potential drop across the solution, and calculate the value of beta A and beta C and ICAR, and then calculate the value of polarization resistance. Next, I want to show you another example. Okay. This is done by another of our research scholar, Ranjit. This is for tantalum dissolving in hydrofluoric acid. In 750 millimolar of hydrofluoric acid, if you take tantalum and monitor the current as a function of potential with a scan rate of 0.5 millivolts per second, you can get this data, and from this data you can get a polarization resistance of 161 ohm centimeter square. Now, if we take impedance data, what we get is shown here. Solution resistance is not that large, maybe 10 ohms. The polarization resistance is going to be less than 100 ohms. So, we see a much lower polarization resistance in this case from impedance data compared to the polarization resistance from the linear polarization experiment, and that cannot be explained using the solution resistance. So, what do we do? This is the equivalent circuit we have used. From this you can visually see that it is going to be less than 100 ohm centimeter square. You can actually calculate it and show that it is 84 ohm centimeter square. It is nearly half of what you get from linear polarization data, and that makes you think, why is it different? The mismatch between LP and EIS is quite large. Now, you can visualize linear polarization as a EIS experiment at some frequency. Now, if we do EIS with 20 millivolt amplitude and compare two frequencies and two scan rates in linear polarization. Now, if you are going to do linear polarization, potential will change at 0.5 millivolts per second. If you go for 0 to 200 seconds, this is how the potential would change. That is given by the green color line, dashed line. If you are doing EIS experiments at 5 millihertz and 20 millivolts amplitude, the amplitude and frequency both are important. Okay. Then if you look, the red color line which shows the sinusoidal potential is more or less overlapping with the green color line, not exactly, but it is somewhat similar up to nearly 1/4 of this cycle. This is one full cycle, half cycle, and this is 1/4 of a cycle. EIS at 5 millihertz, this is 0.3 millihertz, 5 millihertz comes somewhere here. So, if I do linear polarization experiment at 0.5 millivolts per second, that is similar to doing EIS at 5 millihertz, and at 5 millihertz this data has not settled, it has not come to the real axis. So, I cannot take this data and tell that that is going to be low frequency limit and that is going to be polarization resistance. So, looking at this EIS data, anybody can tell somewhere here the impedance has settled, somewhere here the value is probably 180 ohms, you can actually calculate the number, maybe 200 ohms, but you can definitely say it has not settled there. At close to 0.5 millihertz, I can claim that this data is settled and this is probably the polarization resistance or polarization resistance and solution resistance put together. Now, if I draw a sinusoidal wave of 0.5 millihertz, goes from 0 to 2000 seconds, and draw linear polarization at the rate of 0.05 millivolts per second, this is how it will appear. That means 1/4 of a cycle will roughly match with the linear polarization. So, if I do 0.05 millivolts per second, linear polarization at 0.05 millivolts per second, then I should expect to see a polarization resistance close to 84. So, normally one would think 0.5 millivolts per second is low enough for linear polarization experiments, but looking at the EIS data helps you understand what scan rate is suitable or sufficiently low to perform LP experiments for a given system. Okay. So, EIS helps us identify or choose a scan rate for linear polarization experiment. So, out here if you see current versus potential, 0.5 millivolts per second is the black color line. If I go to a slower scan rate, I actually see the current is more. Current is more meaning either magnitude is more. That means the slope is more, inverse of the slope is less, and the estimate from this says 72 ohm centimeter square, which is lot better compared to 161 ohm centimeter square. So, slow rate and accounting for our solution, we get 72 ohm versus 84. It is still not exact match, but it is close enough. Without looking at the correct scan rate, if you just do it at 0.5 volts, 0.5 millivolts per second, saying in literature a lot of people use this, therefore I use this, then you will not be able to explain the difference between the polarization resistance obtained using EIS and obtained using linear polarization. Next, I want to describe a technique called harmonic analysis. Okay. The idea is this: we normally apply a sinusoidal potential, monitor the current, and we know the frequency at which we apply the potential. We do Fourier transform, we do phase sensitive detection. In any case, we want to find the component of the current at that frequency. Okay. What if we apply little larger sinusoidal potential, okay, moderate amplitude, measure the response at second and third harmonic. If you apply a large amplitude perturbation, you will definitely get a good signal at second and third harmonic, you might get some signal at even higher harmonic. But if you apply it moderate amplitude, if you assume that this equation is valid, okay, you can do the following. Okay. This was proposed in 83 and also extended in 94. If you take this, expand this in Taylor series and then write the current as I0 corresponding to DC, I1 sin omega t plus I2 sin 2 omega t plus phi, of course, it may become cosine, okay, plus I3 etc., etc. Then after expanding this and doing some algebraic rearrangement, one can show that the I car is going to be related to I1, I2 and I3. Beta A and beta C can also be obtained from this. Originally it was given as I1 square, but then later I think Dyad et al. Showed that it has to be corrected, and there is a term 3I3 which has to be added to this to get the correct expression for corrosion parameter. Corrosion parameters I car, beta A and beta C. Now, since we measure I1, I2 and I3, it is possible to estimate 3 parameters I car, beta A and beta C. This is obtained by taking this expression, expand in Taylor series, truncate after 3 terms and then rearrange. Since we record 3 points, 3 data points, we can calculate 3 parameters. Now, the advantage is it is still not very large amplitude, it is not like potential dynamic polarization. You can stay within 20-30 millivolts, so you do not disturb the system that much, and you can still get all the corrosion parameters, that is ICAR, beta A, beta C. Whereas with linear polarization and impedance spectroscopy, you can get only RP. Now, there is a problem. The second and third harmonics are usually small, so in presence of noise, getting good quality reliable data from this is not that easy. So, we have poor signal to noise ratio, and if I say I will crank up the voltage, I will get better signal to noise ratio, then we can't truncate the Taylor series after 3 terms. It is still possible to analyze assuming that the basic equation is valid, but you will have to get expression in terms of modified Bessel functions and use some numerical method or optimization program to extract the parameters. Okay. There is no expression which will give you ICAR beta A, beta C in a fashion similar to this. You will have to use an optimization program and get this. Another thing is, this particular analysis does not tell you which is beta A, which is beta C. Okay. It just tells you plus or minus, and you will have to have some idea about the system, but actually if you measure the phase, it should be possible to tell which is beta A and which is beta C. If you do not measure the phase, you will have to have some idea of whether cathodic reaction is fast or slow, or anodic reaction is fast or slow compared to the cathodic reaction. So, we can apply large amplitude perturbation, but truncation is not going to be correct, and it is possible to do numerical program and optimization and get these parameters, but it is not very straightforward. So, another technique that is suggested is called electrochemical frequency modulation. Okay. This was suggested in 2001 by Bosch et al. The idea is this: instead of giving one sinusoidal potential, you can give 2 sinusoidal potentials simultaneously, add them up and apply. Again, use moderate amplitude. Okay. Now, what will happen is you will get the results, you will get second harmonic, you will get third harmonic for each of these frequencies. In addition, you will also get something called intermodulated frequency or interaction effects. So, the potential is not just sinusoidal, it is EAC 0 sin omega 1 t plus sin omega 2 t, and you can again expand this. We do not apply any DC bias, so it is going to be at open circuit potential. This has to be moderate, so that Taylor series can be truncated after 3 terms. Now, the results you get will contain omega 1, 2 omega 1, 3 omega 1, omega 2, 2 omega 2, 3 omega 2. In addition, omega 1 plus or minus omega 2, 2 omega 1 plus or minus omega 2, omega 1 plus or minus 2 omega 2, and of course, even higher ones, but we will say that they are negligible. As long as the amplitude is moderate, it should work okay. In general, one should be able to use this technique with even different amplitudes for this different sinusoidal waves, different frequencies. That is, instead of saying it is EAC 0, I can write EAC 0 1 sin omega 1 t, possibly even plus phi 1 plus EAC 0 2 sin omega 2 t plus phi 2, but then it becomes very complex and it is not necessary, but it is just possible, you should be aware of that. Now, the advantage over the harmonic analysis is this: even if higher harmonics are small, at least it is possible to get reasonable magnitude for the intermodulation frequencies. They are likely to be of moderate quality, moderate signal to noise ratio. So, hopefully, we will get accurate estimates of ICAR, beta A and beta C. So, just a quick representation of how it is done. You have 2 sinusoidal perturbation, we take a nonlinear system, we take two sinusoidal perturbations, add them together, this is how an example wave would appear. And if you apply to a system which follows this expression, then the current would appear like what is shown in the green color line here, and then subject it to FFT, you will get magnitude versus frequency at DC I omega 1, I omega 2. These are intermodulation frequency results. This is second harmonic, this is third harmonic. So, you can see that this is of course a noise free system, ideal system. Results at intermodulation frequency will have little better signal to noise ratio. And after expanding, what Bosch et al. Have proposed is given in the black color font here, but our group has identified some small mistake there, and that correction is given in the red color font here. So, ICOR has to be corrected, beta A and beta C has to be corrected. Bosch et al. Have assumed that beta C is always greater than beta A, but if you monitor the phase, it should be possible to identify which is beta A and which is beta C. Now, we measure minimum 5 data points. We measure I omega 1, second harmonic, third harmonic, and omega 1 plus or minus omega 2, 2 omega 1 plus or minus omega 2. Go back to the previous expression. Out here, if you look at ICOR, if you look at beta A, beta C, you have I omega 1, and that is supposed to be equal to, actually I omega 1 is supposed to be equal to I omega 2 in terms of the magnitude. Okay. We do not use I of 2 omega 1 or I of 3 omega 1 or 3 omega 2 or 2 omega 2. We do not use the higher harmonics to estimate this. That means, if the higher harmonics have little poor signal to noise ratio, you should still be able to get a decent estimate for the ICOR and beta A and beta C. Since we measure at least 5 data points, omega 1, second harmonic and third harmonic, we should be able to get few more expressions. We got 3 corrosion parameters, ICOR, beta A, beta C. We can develop 2 more relationship, and these are called as causality factor by the authors. So, one relationship uses second harmonic, another uses third harmonic. So, if you take the ratio of I omega 2 plus or minus omega 1 to second harmonic, it should come as 2, and if you take the third harmonic, it should come as 3, and they call the causality factor 2 and 3. However, if beta A is equal to beta C, then you would get an expression saying 0 by 0. Obviously, you will have some noise in the system. So, unless the instrument is very precise, you are likely to get some small value here and some small value here, which means the ratio will not be 2, it will be some number, random number or arbitrary number. Okay. But causality factor 3 is probably reliable. So, if CF2 comes as different from 2, you may or may not have to throw away the information. If CF3 comes to be significantly different from 3, then maybe that analysis is not reliable. If the noise is high, you will have to increase the perturbation potential. EAC 0 has to be increased, and this formula cannot be used, but you can expand in modified Bessel function and use optimization program to get it, always assuming that the Tafel expression is still valid. Okay. Now, if solution resistance is high, this will definitely cause an error, and that is lot more challenging to model. Okay. In this case, it is assumed that the current through the double layer is negligible. If the frequency chosen is small, it will be okay. What is small? Maybe 1 millihertz is usually small enough, okay, but it will take long time, and if you want to acquire this data quickly, you will have to go to a little higher frequency. Typically 2 and 5 hertz are used, sometimes 0.2 and 0.5 hertz are used, and double layer capacitance current may not be always negligible. Okay. And corrections have to be employed to account for solution resistance and double layer capacitance. Okay. So, in summary, this is a new method. it can be used in certain cases. Usually when corrosion current is large, this is good. When corrosion current is small and if the noise is high, you will have problem in interpreting this data correctly. So, corrections are needed to the literature formula even under the assumption that solution resistance is negligible and AA capacitance is not contributing that much to the current, and you have to use it with care. Okay. We will stop here today.